Hi, we are Group 7 and our topic is stock price prediction. I'm Supriya Parthiban. Stocks are shares of a company. Buying a company's stock means you own a part of that company. Broadly, stock market analysis is classified into two parts, fundamental analysis and technical analysis. Fundamental analysis involves analyzing the company's future profitability based on its current business environment and financial performance. Technical analysis, on the other hand, includes reading the charts and using statistical figures to identify the trends in stock market. Here, we mainly concentrate on the technical analysis. We try to predict this by starting with some basic machine learning algorithms and neural networks. The dataset here is a dataset from Shanghai City Company. The dataset has 10 attributes and 6,109 instances. There are no missing values. The dataset contains values from 1990 to 2015. The columns open and close represent the starting and final price at which the stock is traded on a day. High, low represent the maximum and minimum of the price of the share of the day. Data pre-processing is run and we drop some unrequired columns to reduce complexity. It can also be observed that it's a time series dataset where the first row contains the oldest stock price. It would be better if we could predict values for recent stocks and train the models on the past prices. Traditional models. We started with some basic algorithms. The most basic machine learning algorithm that we tried implementing on this data is linear regression. The second algorithm was support vector machine with radial basis function as kernel. Support vector machine is used in analyzing the relationship of factors predicting the stock performance. Random foresters, although generally considered a classification technique, but regression is something that random forester can handle. The last algorithm we used was gradient boosting for regressor. Another interesting machine learning algorithm that we used here is k-nearest neighbors. Based on the independent variable, KNN finds the similarity between new data points and old data points. We also use moving average. Averaging helps us understand the data better. It also gives a better idea about the trending of the market. We have used moving average to smooth the price data to form a trend following indicator. These models do not directly predict the price but rather define the current direction. They also help in filtering out the noise. The next algorithm that we used is ARIMA or autoregressive integrated moving average. It is a very popular statistical method. It contains three parameters P, Q and D. So let me demonstrate the code. We use libraries like Panda to read the CSV file, NumPy to perform calculations, and scikit-learn to build predictive models, sklearn, and many more. We first load the dataset and set date as the index, and the data preprocessing is done. We use different techniques to predict the highest price of each day of the stock. While splitting the data into train and validation, we cannot use random splitting since that will destroy the time component. The linear regression model, SVM model, forest regressor and a gradient boosting regressor are chosen to be compared. The training data is given to all four of the models and then we pass the testing data and obtain the predicted values for each model which we use to plot these graphs. Using the subplot feature, we plot the multiple predicted values for different models to visualize how good the algorithms can predict. We now print the accuracy and can see that random forest model is the best performing one, followed by gradient boosting. For moving average, we use the train and validate data set. The next step is to create the prediction for the validation set and check the RMSE using actual values. For KNN, that is k nearest neighbors, we use the same train and validation set. There is not a huge difference in the RMSE values from the previous model, but a plot from a predicted and the actual value should provide a better understanding. The last model that we use is AutoArima. The model has captured a trend in the series but is not efficient. The RMSE value is too high. This is the demo of the basic algorithms we have used. We can safely say that regression algorithms have not performed well on this dataset. The model overfits making these not accurate. All traditional predictive regression models face significant challenges in out-of-sample predictability tests due to model uncertainty and parameter instability. Price movements of stocks exhibit noise from one moment to the next. While a given overall trend may be upward, it can see temporary dips along the way. Predicting these fluctuations and guessing their direction is a key part of the challenge we set for ourselves. To achieve this, we applied neural networks.
Now let me introduce LSTM model. When we introduce this model, RNN suffers from vanishing gradient points problem. This problem causes RNN to have trouble in remember values of past inputs after more than 10 time steps approximately. LSTM is then designed to solve this vanishing gradient point problem in RNN. LSTM has the capability of bridging long-time lags between inputs. You can think of LSTM as a special type of RNN. The key idea is to use memory cells and gates. We can use this formula to implement it. In this formula, FT is called forget gate vector because it determines which components of the previous states and how much of them to remember forget. HT is called the input gate vector because it determines which components of the input from HT-1 and XT and how much of them should go into the current state. OT is called the output gate and control which components of the state vector CT and how much of them should be opted. Now I will show you our code for LST model. And for a single LSTM cell, we use its core function to perform an operation just one step ahead of the sequence time. For example, if our sequence length is 10, it is necessary to call 10 call functions, which is troublesome. In this regard, TensorFlow provides this function, which is equivalent to call time step call functions, that is h1, h2, hn is obtained directly by h0, x1, h2, and xn. And this is our tree model. We use square laws as our loss function and use atoms as our optimizer. And this is our predict model. We use mean square error and as our matrix. In this picture, the red line is our prediction and the blue one is the actual value. And also we can say that in the next period, the stock has a downward trend. Next, I will introduce a deep RNN model. Up to now, we only discussed recurrent neural network with a single unidirectional hidden layer. In it, the specifically function form of how latent variables and observation interact was rather arbitrary. It isn't a big problem as long as we have enough flexibility to model different types of interactions. With a single layer, however, this can be quite challenging. In the case of perceptron, we fix its problem by adding more layers. This picture is the architecture of deep RNN model. In deep neural network, there are multiple members of hidden layers. A recurrent neural network has a recurrent connection as the hidden layer. Each hidden unit is connected to itself and also as well as to other nodes in the hidden layer. So basically, deep recurrent neural network means multiple recurrent hidden layers in the network hierarchy. And we compute the hidden layer of layer 1 as before using ST as input. For all subsequent layers, the hidden state of previous layer is used in its place. Finally, the output of the output layer is only based on the hidden layer L. We use the output function G to address it. Just as multiple layer perceptions, the number of hidden layer L and the number of hidden units H are hyperparameters. In particular, we pick a regular RNN to implement the model. Now let me show you my code. Many times the capability of a single layer RNN are limited, and we need multiple layers of RNN. After inputting X into the first layer RNN, the hidden layer state H is obtained. The hidden layer state is equivalent to the input of the second layer RNN. The hidden layer state of the second layer RNN is equivalent to the input layer of the second layer RNN, and so on. In TensorFlow, the RNN cell can be stacked using this function, and also this parameter is the size of the layer we define it into, and also the output of this function is a tensor, so we need to reshape it to calculate. And this picture is our result, and the MSE is 0.01956, and we can make a comparison between LSTM model and the deep RNN model. So we can see that the deep RNN has a better performance in this dataset.
Now I will introduce RNN part of our project. Our project aims to input a period stock price to predict the trend in the future. We know that the stock data is sequential, which means that the price of stock for today depends a lot on the price yesterday and the price 2 days ago. In traditional machine learning methods, all input and output are independent to each other. They ignore the sequence of the data, so they are not suitable to predict stock value. Recurrent neural networks are models which can capture the dynamics of sequence via circles in the network of nodes, so they are powerful to deal with sequential data. This is the main structure of RNN. The circle of H represents state and each time step. We can see that the current state is not just based on the input data X, but also depends on the previous hidden layer H. Every time step, the transition function is same, which makes function learnable. This is the transition function formula. Now I will show you how to implement RNN by TensorFlow. And this is the main part. First, we call the basic RNN cell and set the hidden layer unit number. We can use call function to implement step by step. For example, if I input x1 and initial state h0, then I will get output y1 and the next state h1. If we want to implement multiple time steps at once, we can call dynamic RNN function. Using this function, we input initial state h0 and a sequence of x. Input x, we can get each state. Now I will show you the code part. You can see this is our dataset after pre-processing. First, we divide the dataset into training side and testing side 9 to 1. And the bench size represents the number of benches. Within a reasonable range, the larger the bunch size makes the direction of the drop more accurate. The time step represents the length of each sequence. It determines the subset of the local optimum that the algorithm can coverage to. This is the bunch normalization function. We use it to normalize for each training mini-bunch. After that, we split the features and labels in our training and testing dataset, and we get the bunch index. Then we can build our RNN model. First, we need to set some parameters: the hidden layer unit number, the input and output dimension, and the learning rate. After that, we need to initial the matrix of weights and binds, assigning random values to them. The in represents connect the input and hidden layer, and out represent connect the hidden and output layer. Then we build the RNN model. First, convert tensor to two-dimensional and input it to hidden layer. Then convert tensor to three-dimensional and input it to RNN cell. Next, we call basic RNN cell function and the dynamic RNN function, as I explained in slide. Then we multiply the weights and add the binds. We can get a predicted value. Then we can train our model. First, define the loss function, and we use Adam optimizer to minimize our loss. We fit the training features and label. We run 600 times and print the loss every 10 times. We can see that after 600 times training, the loss is very small. Finally, we can do prediction using the trained model, and we also use mean square error to evaluate the performance of our model. We can see the mean square error of our model is around 0.01. We can see the true value curve in red and the predicted value curve in blue. The two curves almost coincide.